And one thing you can do with these properties is, well, what properties just depend, what extra equations or features depend just on those properties, not on the particular version. So there's a number of consequences. For example, you can show that just based on those properties, that say 0 times any vector equals the 0 vector. Okay, so we're not taking a particular form. We know it's true for particular forms, but then we can say just, so the game you're playing in this proof is, show this is true just from the properties. Well, and you can see here in this little proof given here, that you start from any vector equals 1 times v. That's one of those special properties. But then I can say, because that 1 plus the number 1 is equal to 1 plus 0 times v, right? And then I can use the distributive property to multiply v in here. This is equal to 1 times v plus 0 times v, and that 1 times v equals v. So I've shown in this little thing here, just using these properties, that for any vector v, v equals v plus 0 times v. The whole, there's not a vector there. Sorry about that. This is 0 times the vector v. Well, we wanted, the point of this rigmarole was to get this thing in place. And then what I can do is, well, I know that there's an additive inverse of this. There's a vector w, so I can say w plus v equal, I'm choosing this to be the inverse, so this is equal to w plus v plus 0 times v. And then I have the 0 vector equals, using associativity, w plus v plus the number 0 times the vector v. And that w plus v was the 0 vector. And then 0, the vector plus 0 times vector is equal to this same vector, 0 times vector. So you end up with the final result by just playing around with just the basic properties of vector spaces. So we know that it doesn't depend on the particular version. You can say 0 times any vectors gives you the 0 vector. Okay, you can do the same thing here, that minus 1 times v is going to always be the additive inverse of v. And you can show that r times the 0 vector equals the 0 vector. Using it gives the same kind of little sort of, the game here is to show that it just depends on those basic properties in this list up here. Well, it's too far back to scroll down. So you have these first consequences, right? And then also every vector has a unique inverse. So it's given the fact that if there's not going to be more than 2, there's just going to be one of them. And since you know it's minus 1 times the vector, you've got a handle on the inverse. Okay, so there's some example problems here, but the next topic is subspaces. Now we're going to sort of mainly deal with this next time, but let me just come in with the word subspace. It's got 2 words here, right? Sub and space. Well, the space part is really short for vector space. This is sort of a new topic here. Vector space. And the sub is short for subset. So you've sort of chopped out the set and you've chopped out the vector, and you're just left with subspace. So what is a subspace? A subspace is a subset of a vector space that is itself a vector space under the same operations. Under the same operations that made the big space under the same, you have to use the same operations for the subset and the enclosing space. You can't like change the definition. But that's what a subspace is. So it's a vector space. It's a subspace of a vector space that is itself a vector space. Now, just to make this more concrete, we have these big spaces, like say RC3, which is the space of all these things here, right? So we can say, well, you know that any linear system is going to have a subset of vectors. So we could say, well, one form of this would be 1, 2, 3 times X plus 3, 4, 5 times Y, such that X and Y are real numbers. Well, you can see that this is a subspace. This is not all the vectors in here, right? But it's going to have a lot of them. And it's going to turn out that this is a subspace, but it's also going to be a vector space. And you can see it looks like the solution set of a homogeneous linear system. So that when we talk about subspaces, that's going to correlate with solution sets of homogeneous linear systems. So here's a subset. You know, you have XYZ, you have a one equation linear system, and so that it turns out that under the same operation of adding vectors and multiplying vectors, this is a subspace. Now, so you can go through and show all the properties, but it turns out, and this is going to be a theorem or result, that the only thing you really have to show that this subset is a vector space is that it's closed. Meaning, if I take this definition and I add these two vectors and I get a vector that's back in the same space, this space is going to have all the properties of a vector space. I don't have to check all 10 of those properties. I know just from that one thing. So I can check, I'd have to take two of these things here, X1, and add them, and then say, okay, if these two are in this space, this one is in this space. But what does that mean for these two vectors here, the 1 and the 2, to be in this space P up here with X plus Y plus Z equals 0? Well, it has to be that X1 plus Y1 plus Z equals 0, if this is in the space, and it has to be that X2 plus Y2 plus Z2 equals 0, if this one's in the space. But then we have to show that on that basis that the components also do this. Well, if we add up X1 plus X2 plus Y1 plus Y2 plus Z1 plus Z2, then you rearrange it into X1 plus Y1 plus Z1 plus X2 plus Y2 plus Z2. And using these two properties, that's the same as 0 plus 0, which is 0. So this shows that if I add two vectors, I get this constraint works. Now, if I put a 1 here, this wouldn't work. So if I put an inhomogeneous linear system up here, this is going to fail to be true. Okay, so this isn't trivial that this it only works for homogeneous linear systems. It doesn't work for general ones. Here's another simple linear system. One of the things is that it turns out that a vector space itself is a subset of itself. It's a vector space, so the whole space is a subspace. So if I take any vector space V is technically a subspace, right? But it's not a proper subspace because it's the whole thing. So if you have W, a subset of V, and W is not equal to V, and W is a subspace, then it's a proper subspace. Okay, just because you're more interested in proper subspaces is the term. So, okay, the other one is every subspace has a zero space, right? So this is because the zero vector is a subvector of V, so the zero space is a subspace of every vector space. Okay, so these are just sort of some features of what you're beginning to get from your definition. And here's what you call the subspace tests, that you're saying, okay, there's three things that are equivalent. They're just, it's like the first one is your concept. S is a subspace, like for a non-empty subset S of a vector space. Under the inherited operations, that's the same ones in the vector space. The following mean the same thing. S is a subspace of that vector space. That's the concept, right? We have a definition for it. But the concept is not really a good test. We want to have a simple way of doing it. Well, it turns out that if S is equivalent to that, S is closed under linear combinations of pairs of vectors. Okay, so we take two vectors and two scalars and say, if this linear combination is an S, it's a vector space. Okay, now S is closed under linear combinations of any number of vectors. This is 3 is a generalization of 2. Well, it's clear that this is a useful feature, but it's just an extension of 2. So 2 is going to end up, you can use 2 to show that 3 is true. The crucial thing is to show that 1 and 2 are equivalent. Okay, because then we have a test. We can say, if I give you a subspace, and I give you a subset and ask you, is this a subspace? You can just apply number 2 and calculate this linear combination and show that it has the property of being in the set. And then you know that S is a subspace and has all those 10 properties and everything acts like a vector space. Okay? So a concept and a test. And that's what the point of this is. So we can, I think, we're going to deal with spanning sets are someplace that a lot of people have trouble with, although it's a simple idea. But let's go on and see if we can deal with that next time and do an example here. Because what we're looking at, let me see, let me